water. These two natural resources were indispensable to the pioneer and often determined the location of frontier outposts. As the years passed, new fuels and building materials lessened the need for wood in daily living, but not so for water. The ever-increasing growth in population, the added needs of industrial plants, hotels, large department stores, and many other factors are rapidly diminishing an already inadequate water supply. In many communities, this condition has become critical. Fine parks are taken for granted, with green lawns, trees, and shrubs, but seldom do people realize the enormous quantity of water required for maintenance. The watersheds of neighboring mountains provide the water supply for many cities. Almost 80% of the available water is surface water from the runoff of melting snow and rain. Only about 20% is obtained from underground sources such as deep wells. So if rainfall has been scarce, the melting snow is depended upon to satisfy the needs. Yes, melting snow adds much needed water to the many gullies and streams, but many of these precious gallons are lost. Almost 3/4 of the original rain and snow moisture are dissipated through evaporation and transpiration. Even more is wasted through uncontrolled runoff. An adequate water supply can be established only through conservation, and one method is to do as the beaver does. Build a dam, or as the old-timers used to say, a cup for Adam's ale. Dams don't just happen, they are planned. First, a potential site must be found, such as this area near Denver, Colorado. The impounding possibilities, geological formations, present habitation, and transportation routes must be studied before any construction is started. Access roads are an immediate need for the movement of thousands of tons of building materials and equipment. The roads are not constructed as thoroughfares, but to provide access between the main highways and the dam site. Prime clearing of the roadway is done with heavy bulldozers that push aside rock, dirt, brush, and trees. This stand of timber is no match for these steel monsters. With the heavy dozing completed, it takes very little effort to do the final grading of the roads. Where roads needed widening past rock outcroppings, Gardner-Denver wagon drills powered by portable air compressors moved in. After drilling, the holes were loaded with powder and the rock blasted away. With the completion of the access roads, equipment and workers will soon be moving in to the dam site. Without this vital road system, construction work could not even start. The construction of a large concrete dam sometimes involves years of labor for many people. Generally, the accompanying influx of workmen and their families causes a housing shortage in the usually small communities. Semi-permanent homes are the answer to this problem, and often hundreds of these units will be found near a dam project. A headquarters building from which all construction is directed houses the engineering and office staff. A maintenance shed is a must, as equipment breakdowns can cost thousands of dollars in delays. The stockpile area begins to accumulate the supplies necessary for construction. Lumber for the thousands of forms that will be required. All materials must be readily available. Loading crews are kept busy moving equipment in and out to the various job locations. Many of the concrete forms are fabricated in the carpentry shop and stacked nearby in readiness for the day they will be needed. Under this 225-foot stand of rock will lie the diversion tunnel and control valve vault. This overlay of rock will give excellent protection from freezing and aerial attack. After drilling, blasting, and mucking out, the bulldozers start the final cleanup, preparatory to pouring the 2-foot thick concrete walls. Here can be seen 2 of the tunnels. The one to the right is the access tunnel, and the one to the left is the outlet tunnel. During the spring thaws and heavy rains, this placid little stream can become a raging torrent of millions of gallons of water, which will soon be diverted through this tunnel entrance. Diversion of the stream from its normal bed will then permit construction of the dam keyway. If there were such a thing, we might call this a mole's eye view of the outside of the diversion tunnel. From the entrance to the discharge portal, it extends 800 feet through the mountain. It has an access tunnel 90 feet in length for servicing. The valve vault is 58 feet by 19½ feet. Looking inside the control valve vault, we find the water is channeled around concrete islands through the control valves to the outlet portal. These 4 42-inch automatic outlet valves will pass the natural flow of water at a rate of up to 1,200 cubic feet per second at normal water level. Final cleanup work is underway on the diversion tunnel exit. The sides of the flume must be ground smooth. Rough areas left by the concrete forms could cause undesirable turbulence and water retardation. In some cases, it was necessary to practically move the top of a mountain. When such conditions presented themselves, wagon drills were moved in. Thousands of holes were drilled and blasted, as the main excavation consisted of some 200,000 cubic yards of rock, sand, and dirt. This particular area is the site of the crusher, screening, and batcher installations. When the area is too rough for wagon drills, handheld drills are used. These lightweight portable units are lifesavers under such conditions. To supply the huge quantities of air required by the drills, portable compressors are spotted over the entire job. In some cases, small 125-foot units. In others, batteries of huge 500-foot and larger outfits. After drilling, powder monkeys move in, and the holes are loaded with powder and tamped. They are then wired with electric detonators so as to provide a simultaneous blast of all the powder. After completion of the loading and wiring, all men and machinery must be cleared from the area. Blowing whistles announce the approaching blast. 0 hour, and the shot is fired. Over 70,000 cubic yards of rock have been shattered by the blast. Correct drilling and placing, as well as loading of the holes, means good fragmentation, and good fragmentation means less secondary drilling. Some secondary drilling and blasting is required, but handheld drills rapidly take care of this problem. In preparation for the coming plants, much of this area requires leveling only, and this is no problem for the heavy bulldozers. In other areas requiring removal of the blasted rock, power shovels are used. They load the material on powerful uke trucks, and it's hauled away to be dumped over the mountainside. With the area cleared of excess material, the bulldozers again move in to take over the leveling off process. With the clearing and leveling finished, plant construction can soon start. We will see erected here the many machines and plants required in the preparation of the aggregate and final mixing of concrete. Across the canyon, the work of drilling and blasting on the keyway progresses. Hand drillers retain their precarious perch by means of safety ropes, which, from a distance, resemble an intricate spider web. A slip here without a rope would mean certain death on the rocks below. In diverting this stream through the tunnel prepared for it, it becomes necessary to build an earthen coffer dam. The coffer dam will ensure a dry creek bed for the construction of the base of the dam. It will also allow the continued flow of water to downstream users. A large metal trash rack at the entrance to the diversion tunnel prevents the access of foreign material, which might jam the flow of water. The water from the diversion tunnel flume must be released at the minimum rate of 1,200 cubic feet per second. This will serve the basic irrigation needs of the downstream farmlands. With the coffer dam completed, work begins on mucking out the creek bed. Because of scaling of the keyway, work is limited to the forward area. The creek bed must be cleared down to solid bedrock to ensure the proper bond between concrete and stone for the base of the dam. Erection of the cement storage plant and the batcher or mixer plant is well underway. Soon the combined operations of these two units will be turning out 8-yard batches of concrete for pouring at the dam site. The crusher, screening plant, and raw storage cover a large area. After passing through the primary crusher, the material is carried on long conveyor belts to the screening plant. Here it will be sorted by passing over various sized screens. When completed, this screening plant will convey the sorted material to the raw stockpiles. From the stockpiles, a long conveyor belt, encircled by tubing, will transport the desired type of aggregate to the mixer or batcher plant. Scaling is the final task on the keyway. All of the loose rock is barred free and sent rolling down the mountainside. The batcher plant is now ready to begin combining the thousands of tons of cement and aggregate needed for concrete pouring. Gardner-Denver stationary air compressors furnish the necessary air power for batcher plant and related operations. The air supply must be dependable and plentiful, provided hour upon hour in adequate quantities. Big ukes with rock for the primary crusher slowly grind their way up the twisting, turning mountain inclines. Sure, confident drivers show little concern, handling their mounts as if they were toy cars of Kittyland, and slowly but surely the stockpile at the primary crusher grows. Bulldozers arrange and push the rock into the crusher chute. It takes skill to handle these steel monsters. One false move and thousands of pounds of machine could go tumbling down the mountainside or wedge in the crusher. After passing through the primary crusher, the rock begins the first of its long conveyor journeys in the process of being converted into aggregate. Up another belt and into more machinery. After being thoroughly shaken, screened, and washed, other conveyors carry it out to its proper stockpile. Graded rock will pause temporarily at its stockpile. Soon it'll be moved again, the grade being taken depended on the concrete specifications of the job at hand. Giant earth movers scrape away the surface in preparation of a railroad spur. Here, thousands of tons of cement will be received for transportation to the mixer plant. Across the canyon, we can visualize the vastness of the coming construction work. Falling rock could do serious damage to the compressors if they were not under shelter, and compressors are essential on this job. For instance, they're needed to furnish air to the Gardner-Denver handheld drills that are speeding completion of the excavation for the tower site. After drilling and blasting, the concrete base will be poured and tower cables installed. Soon the huge concrete bucket and other construction equipment will swing its way across the canyon, suspended on long strands of cable that span the length of the dam. Building a dam is a demanding job. Every inch of the work is detailed and engineered to precise specifications. Forms for the concrete are carefully and sturdily built to withstand the heavy pressure exerted by the bulk concrete. Everything is predetermined by the construction supervisors. The bedrock must be super clean. Picks, pry, and whisk brooms brush, all to guarantee a perfect bonding between rock and concrete. Then the final polishing with a high-velocity stream of water, thoroughly cleaning every crack and crevice. Even Junior's face couldn't sparkle brighter. Now the dinkies start shuttling back and forth between the mixer plant and the bucket. This is what everyone has been waiting for, to see the concrete being poured, to watch the dam grow, mix and dump, and every time the dam is 8 yards nearer to completion. In the distance, a lone operator seated at the control tower has at his fingertips the means of placing the bucket exactly where desired. Like a giant lavalier, the bucket wends its way down into the seemingly bottomless yaws of the canyon, and men are there waiting for it, anxiously awaiting the opportunity to empty and return it for another load. On reaching the bottom of the canyon, air pressure is applied, the gate is tripped, and concrete spills onto the base of the dam. A flip of the wrist, and the bucket returns for another load. More than the eyes of a hawk are needed to spot the concrete bucket at its exact location for pouring. A communications system linking the cable tower operator and the 2 bellboys allows perfect placement. Instructions are relayed by phone and a bell code system to the operator high atop the canyon. The coordinated viewing of the bottom bellboy and the bellboy at the top of the dam serve as eyes for the cable tower operator. Layer upon layer, the concrete slowly inches its way upward. Yardage increases with the sole use of the 8-yard bucket for placement, and a smaller one added for utility work. Vibrators agitate and settle each pour of concrete, breaking air pockets formed in the mixture. The mass must harden solidly, free of fractures and cleavages that could weaken the structure. In a project such as this, where thousands of lives could be involved, not even one mistake is allowable. Power saws are used to cut any timber near or below the water line in the backwater section. Trees that would later rot and topple into the water could cause serious property damage. So down they go. Hour by hour, day by day, section by section, the dam grows upward. Prefabricated forms can now be used on some of the work. Teams of steel workers, carpenters, and concrete men coordinate their activities to keep the job moving ahead, eliminating wasted, cost-consuming time. Mix, pour, and vibrate. Mix, pour, and vibrate. That's the tempo now. To maintain consistency of the concrete, thousands of feet of cooling lines are placed prior to the pouring of each lift. Circulating water drops the temperature of the mixture to the desired 45 degrees. Before placement of the next lift, the preceding one receives a thorough blasting with a mixture of sand and water. A pipe fitter's nightmare is the maze of interconnecting cooling lines. Water circulates from 72 hours to 14 days, depending on specifications, allowing ample time for the proper cooling of the concrete. Men, not machines, build dams. Men with know-how and nerve. Like Sam Penna, superintendent of excavation, John McGee, superintendent of carpenters, and Spud Murphy, superintendent of concrete. Men who know how to make the machines perform for them. Men of stamina and decision. Men who can battle the odds of time, weather, and machines each and every day, and win. After pouring each lift, the bucket travels a shorter distance, lessening the time between batches, and construction progresses at a faster pace as the sections move skyward. A plentiful supply of high-quality aggregate is a prime factor in dam construction. It must meet specifications, and in many cases, new sites must be developed, often many miles from the dam site. If distance is a factor, as in the 20-mile haul from this site, larger trucks must be added to cut the time problem and increase the yardage hauled. A single stop, the tripping of a lever, a sudden whoosh, and another 22 cubic yards of aggregate is on its way to the raw storage pile. Now the process of scrubbing, screening, and sizing must go on continuously. A shortage at the raw stockpiles would mean a shortage at the mixer, resulting in a shutdown of the entire operation. Work moves along in high gear at the rate of at least 2,500 cubic yards of concrete poured every day. Over 83,000 cubic yards have been placed, and the pace quickens as the dam decreases in thickness as it progresses upward. Every thought of every individual is aimed in one direction: pour more concrete. Viewed from the air, the reasons for a gravity arch dam become evident. The narrow rocky canyon with its steep walls perfectly fills the bill for this type of construction. The tempo of the entire operation is now aimed at speeding up the pace of the bucket. Reusable forms are jacked in place over and over again. Men and machines seem to become more closely coordinated as the end gradually inches into sight. Mix and pour, and in the background workmen can be seen already pouring some of the final lifts of concrete. However, regardless of the speed up, each lift still receives its abrasive washdown of sand and water. 24 hours a day, 7 days a week, the construction goes on. Powerful floodlights penetrate the darkness of the long night hours, and the men must bundle up against the cold mountain air. This entryway permits access to a gallery running the entire length of the dam. Thus, periodical inspection is provided for, as well as drainage of the water formed by condensation. With the dam at approximately 3/4 of completion, it begins to present an imposing appearance, and we begin to appreciate the magnitude of this operation. However, there still remains many things to be done. For instance, the completion of the spillway. Here, the concrete buckets continue to make their two-way trips, and when completed, this spillway will be capable of handling some 17,000 second feet of water. The excess water not needed by downstream users continues to collect, the first indication of the large lake to be formed. With the spillway now completed and the top of the dam nearing completion, workmen start the job of cleanup. All scrap lumber, steel, and the many odd pieces of machinery must be removed from the area. Finally, topping out day arrives, the day everyone has been anxiously awaiting. The day when the last lift of concrete is to be poured. Dignitaries from the local water board are present, along with news photographers. The last pour starts as the night chill settles over the mountains. The months of labor, the hours of discomfort in heat and bad weather are all overshadowed by the good feeling that comes with the completion of the job. Soon the repetitious mix, pour, and vibrate will come to an end, but there are always hearty men, jovial men, who like to stand around a fire on a cold evening to see the last of the pouring of the some 630,000 yards of concrete. And here it is, the completed dam, soon to be christened Gross Dam. It towers 340 feet between the canyon walls. It is 1,002 feet at the crest and cost approximately $2.5 million. When filled, the capacity of Gross Dam will be about 42,000 acre-feet, or about 3 months' supply of water. Eventually, it may be increased to 113,000 acre-feet. This does not seem at all improbable when we consider that today we are using 6 times as much water as in 1900, and in 1980 we must expect to use twice the volume now being used. In future years, the reservoir could serve recreational purposes, as does nearby Grand Lake. Summer homes cooled by a lake breeze, providing contentment and relaxation for thousands of city dwellers and vacationing tourists. Sailing into a sharp wind, or scooting about the lake with a fast motorboat, seeking higher speeds, sharper turns, or just thrills. A scenic cruise on a pleasant Sunday afternoon. Or Rags and the entire family can brag about the big one that got away. Water, indeed, is the very foundation of our life, whether it be for pleasure or for sustenance. We must conserve and safeguard it. The bubbling, sun-speckled stream is ours to lose or gain. Mistreat it, and it can lead to disaster. Control it, and it will serve us faithfully for many years.